Hello everyone, this is Weinan from Alibaba Cloud. Guocheng and I complete this practice. I will present this session today. Our topic is Speed up the boot time of guests in Alibaba Cloud. This is the agenda of today's session. First, I will introduce the background and why do we need to do this. Second, I will figure out our solution. We call it async DMA map. Third, I will show the guest boot process with async DMA. And then I will list several optimization designs for this practice. At last, I will share our achievements with this solution. Let's start as the background. So, what's the problem? As you know, we need to DMA map all the guest memory when there is a pass-through device, since the devices might DMA to the whole guest memory, and the memory cannot be swapped, which is DMA target. But we don't know what memory is the DMA target. So one simple solution is pin map all the guest memory. It might not be a problem when the guest memory is very small, but as you know, the memory is not a scarce resource today. So a guest might have a few hundred or more gigabytes system memory, and the DMA map is one time-consuming process. Then that will be a big problem. There are two charts to show the impact on the guest boot and QEMU initialization time along with the VM's memory size increase. Let's start at the left one. The horizontal coordinate is the VM's memory size, and the vertical one is the boot time with the unit second. You can see if we assign 8 GB memory to the VM, the whole boot time is around 20 seconds. The boot time will increase along with the guest memory growing up. When the guest memory reaches 300 GB, the boot time of VM will be upon 2 minutes. In this time, the users don't know what happened in the background, and they are also not sure if the creation is still running. That's very bad user experience. We need to figure out the root cause. Then we have the right chart. It shows the QEMU initialization time versus memory size. As you can see, most of the boot time is in QEMU initialization, and most of the initialization time is in doing DMA map. Before we raise the solution, we need to know some conditions. For this problem, first, it means more time cost along with more memory. Second, no DMA, no DMA map. If there are no devices need to do DMA, of course, you don't need to do DMA map. But there is one important information. DMA only touch a specific range of memory at a certain time. It gives us a chance to make optimization. Maybe we don't need to pin map all the guest memory during the creation of VM. Based on the conditions, what options can we have? The first thing that comes to mind is the virtual IOMU or Pyro virtualization IOMU. It should be a good solution, but the implementation is very complex, and it also needs much development effort. So we choose one simple solution. We call it async DMA map. There are two key points. The first one is only map necessary memory first. It ensures the guest operating system boot up. Then maps the other memory asynchronously in the background. It might bring a little perception to the user, but it gives better user experience. This page shows the overview of the memory access with a pass-through device. First, let's talk about the current status of KVM. Let's use GPU as an example. The host pin map all the guest memory before the guest OS boot. Then the GPU driver is loaded, and then the application generates workloads for GPU. When the workloads come to GPU hardware, it might trigger DMA. If the DMA address hadn't been mapped, hardware access error will have occurred. Our solution is adding the virtio-balloon driver. The virtio-balloon and GPU driver both can allocate the system memory. If the balloon driver is loaded before the GPU driver, it can balloon some memory ranges first. Then the GPU driver doesn't have chance to allocate from these ranges. DMA won't happen in these ranges too. So it's not necessary to pin map them during the creation of guest. Map them asynchronously is fun. This page shows the architecture overview. The solution will touch three components of QEMU virtualization. The first one is QEMU. It's responsible for triggering DMA map and balloon change. It's also responsible for tracking the balloon pages. The second one is the virtio-balloon driver. It's responsible for ballooning pages and telling to the host. The third one is the VFL driver. It's responsible for doing pin DMA map. In the QEMU initialization, the backend driver of virtio-balloon in the QEMU initializes the balloon size of guest. When the front-end driver of virtio-balloon in the guest is loaded, it will query the balloon size configuration and try to balloon to target. It needs many loops with a little change one time. Every time balloon, it will send a notification to the host. The backend driver receives these notifications to track the balloon pages. They are used for generating the balloon page table in the host. The whole page table is generated after it is finished. The QEMU calls DMA map for the memory ranges beyond the page table first. The other memory ranges in the page table can be mapped asynchronously. How about the communication channel of virtio-balloon? This page shows the related functions and struct. The communication channel is ready. The only thing we need to do is recording the balloon page's address. There are two word queues named inflate VQ and deflate VQ. The front-end driver uses the inflate VQ and deflate VQ to send notifications to the host. One handler is attached to these two word queues in the backend driver. That is virtio-balloon handle output. We can get word queue element in this handler. It contains the guest PFN and page number information. So everything is ready. Just add a simple recording logic. This page shows the balloon range tracking workflow. It's also very simple. In the inflate process, the front-end driver sends an inflate notification by inflate VQ. Then the back-end driver receives it and dispatches it to the handler. The back-end driver tracks all the inflate pages and gets the GPA by PFN. Then adds them into the balloon page table. In the deflate process, it's similar to inflate. The only difference is the backend driver needs to remove the released pages out from the balloon page table. This page shows one whole picture of the guest boot process with async DMA map. There are three phases. Phase 1 is initialization. Phase 2 is DMA map asynchronously. Phase 3 is completion. Phase 1 begins with the QEMU initialization. The QEMU initializes the virtio-balloon size. Only leave necessary memory for the guest. Then it performs DMA map below 4 GB as usual. Then let's turn to the guest view. The guest OS will enable the virtio-balloon driver first. Then it queries the balloon configuration and begins to inflate the balloon to the target. It will call fill balloon to allocate pages and tell the host the PFN of the balloon pages. The backend driver receives this notification and uses the PFN to generate the balloon page table. After the balloon process is finished, the host will know all the balloon memory ranges. Since the balloon memory won't be allocated by other devices, so DMA won't happen in these ranges. So QEMU can only map the memory ranges beyond the page table. Then the pass-through device driver is loaded as usual. Phase 2. QEMU triggers deflate balloon step by step. The front-end driver of volatile balloon receives this event will call leak balloon to deflate. As same as inflating process, QEMU can receive the deflate notification and get the released pages PFN. Then QEMU updates the balloon page table and trigger DMA map of the released pages. After the balloon is empty, everything is back to normal. During the practice, we met several problems. Then we have some optimization design for these problems. The first one is auto-combination during the inflating process. The problem is the balloon driver only allocate one small page at a time and send a notification to the host every 1 megabytes. The QEMU will get huge number of pages. The best method is combining the adjacent pages and create bigger memory range in the balloon page table. Actually, most of the memory ranges are adjacent, since the balloon driver is loaded very early and most of the memory is free. After the deflating process finished, QEMU triggers DMA map of all the memory ranges beyond the page table. It can reduce the DMA map times. Second optimization design is increasing the balloon page size. Here is the source code in Linux kernel. You can see balloon page alloc only allocate one page at a time. 4K page is too small for the current virtualization environment. That will import heavy but unnecessary communication between guest and host. If the guest has a few hundred or more system memory, just make a little change to use alloc pages to alloc one large size of memory. For example, allocating 2 megabytes inside of 4K makes the communication much more efficient. One-time volatile talk can inflate or deflate 512 megabytes memory. It can reduce the communication frequency significantly. The third optimization design is pre-map. The async DMA map can start early, independent of deflating notification. QEMU triggers async DMA map step by step. If there is a new notification from deflate VQ, which contains the released pages information, check if they are in the mapped range. If not, then map these pages and give AC key to the guest. This optimization design can speed up the async DMA map process. Last, let's see what are the achievements of this practice. This test result is based on the initialized balloon size. It's set as 8 gigabytes. You can see the QEMU initialization time is still around 7 seconds, although the guest has more than 300 gigabytes system memory. The watch create command can return back very quickly. Okay, then let's see the guest boot time versus memory size. The boot time of guest hasn't increased along with the memory size increase. You can see the boot time keeps around 20 seconds, even though the system memory is upon 300 gigabytes. So the result shows that this practice can speed up the boot time for guest significantly. Okay, that's it. Thank you.